Hi everybody, welcome to this video on bond making and bond breaking calculations. This is a follow-up to the exothermic endothermic reaction video that is on the channel as well, and I'd recommend watching that video before you do this one. This is looking at the actual calculation to calculate whether a reaction is exothermic or endothermic, and it involves using the numbers provided in the exam that will allow you to see the energy needed to break a bond. Now, before we do that, we're going to just do a little bit of background about bond breaking and bond making and why the numbers are positive and negative and what that means. So first and foremost, we've got on the screen an oxygen to oxygen double bond. Now, if I want to break that, I have to put energy in to break that double bond. Now, we say that that is a positive number, and it's positive 498 kilojoules per mole. So what that means is for every mole of oxygen molecules that I have, I'm going to need to put in 498 kilojoules to break those oxygen to oxygen double bonds. Okay, so it's a strong bond. Now, the second part of this, and this is quite important, is if the bond was to form between two oxygens and it was to make an oxygen molecule, then that would be a negative number, as that would release 498 kilojoules per mole of energy. So the first thing you'll probably notice on the screen is that you've got two numbers. One of them is a positive number, which is the energy needed to break that particular bond. And then the other one is a negative number, which is the energy released when that bond forms. Now, when you look at your bond energy tables, you will always see the positive values are the ones that are given to you. So you're 99% of the time going to be given a bunch of numbers, and they will all be to break that bond. So you might get a carbon to hydrogen as a positive number, and it will be a value required to break that bond. What you've got to know, and the examiners won't tell you this, you need to know that if that bond was ever to form, then that number would be negative, okay? Because energy is released when bonds form. Energy is required to break bonds, and that's a really important part of what we're going to do when we do the calculation in a minute. So just be aware, to break a bond, it's going to be positive, the value of the bond strength. And then when a bond is made, you get negative the same value. Okay, so that's the key thing. Right, so we're going to take a look at our first example, which is a bond making, bond breaking calculation. It's a fairly simple one to start with, just to get you into the routine of how to do these. So the first thing I like to do is, with a highlighter pen, is I highlight my reactants in one colour. Okay, so my hydrogen and my chlorine I'm going to highlight yellow. And then essentially my products, in this case I'm going to highlight pink. You don't have to use pink and yellow, just two different highlighters, absolutely fine. And then what we will do is we'll proceed to work out the first part, which is my bond breaking. So this side here is my bond breaking side. Okay, so these are the bonds that I'm going to have to break first of all. So hopefully we can all see there's one hydrogen to hydrogen bond, which is equal to 1 multiplied by 436. And then I've got 1 chlorine to chlorine bond, which is 1 multiplied by the value of that, which is 242. So I've broken the hydrogen to hydrogen and I've broken the chlorine to chlorine. And that's it, there's nothing else to break. So when I total them together, it should give me 678 kilojoules per mole. Now, because I'm breaking bonds, that's going to have a positive number in front of it. And that's important for that next bit. So when I go to my product side, I'm going to have a slightly different situation, because this one is the bond making side. Now, on the bond making, we have to be very, very aware that all of the numbers that I'm going to use are going to be negative because of their bond making. So in the table above, all of the values are the energy required to break that particular bond. If I need to make that bond, I make sure the same number is there, but it's a negative sign in front of it. So in this one, I've got 2 HCl's. Okay, now the HCl has a bond strength of 431, so it's going to be 2 multiplied by minus 431. Now that is super important because that minus sign there is purely there because we are making bonds. Okay, that's really, really important. So the 2 times 431 will come in at 862 minus 862, should I say, because we've got a bond making occurring on the product side. So those negative numbers are used for bond making, positive numbers are used for bond breaking. Now that's important because when we do the next bit now, the energy change, so when I work out the energy change for this reaction, what's going to happen is I'm just going to add the 2 numbers together. So I'm literally going to do positive 678 plus a negative 862, and that will give me minus 184 kilojoules per mole. Okay, now there'll be some of you thinking, when you've been taught this, you'll have been told to do the reactants minus the products. Now, in all the simple examples, that will work. Okay, doing reactants minus products is absolutely fine. There's nothing wrong with that method. The only time that method is going to cause problems is if you're ever asked to find an unknown bond. So if they gave you the answer and said work out an unknown bond strength, i.e. work backwards, then it starts to get very tricky if you don't employ this method, because you've got to know that bond makings are always negative numbers. So if you've got an unknown bond on the making side, it's going to be a minus. And that's important. We'll look at those examples in a little while. So what I've done down at the bottom, I have basically taken my 2 numbers. I've taken my positive 678, and I have also taken my negative 862, and I've just added them numbers together. I've just taken the sum of them numbers. Okay, and the answer is minus 184. So that's the first example. Hopefully that is fairly easy to follow. That's a fairly simple example. We're going to look at some trickier ones in example 2 next. Right, so we're going to go on to example 2. Now, the first thing you'll notice about this example is the complexity has increased a little bit. Method is still going to remain the same though. We're going to highlight our reactants in one colour. Okay, and then we are going to highlight our products in another colour. So we've highlighted our products in pink, reactants in yellow, and then what we're going to do is we're going to work through our calculation. So the first thing we've got on the reactant side is our bond breaking. So remember, this will be a positive value. So first of all, if you look at the carbon to carbon single bonds, I've got 2 of them. So I've got 2 carbon to carbon single bonds, which is equal to 2 multiplied by 348. And then I'm going to move on to my carbon to hydrogen bonds. I've got 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 carbon to hydrogen bonds, which is going to be 8 multiplied by 412. I've just picked that number straight from the table. And then at the top, I've got 5 oxygen to oxygen double bonds, which I will also be able to get from the table, which have value of 498. Now, just before I total all of these up, I just want to make you aware of something. The molecule has 3 carbon atoms in it. That doesn't mean it's got 3 carbon to carbon single bonds. Whenever you're doing your bonds, you should always be counting how many sticks there are. It's not about how many atoms, it's how many sticks you're breaking. So if you look in between the carbon atoms, I've only got 2 bonds to break, even though there are 3 carbon atoms in there. So what I'm then going to do is I'll add up the numbers and I should, if I've done everything correctly, I've got 6,482, which is a positive number because I've broken bonds. Now, I'm going to go on to the bond making side now. So the bond making side is exactly the same process. Add up the number of bonds, but the bonds will all be negative values. So if I've got 3 carbon dioxides, that's going to mean each molecule has got 2 sets of bonds to break. So in total, I've got 6 carbon to oxygen double bonds, which is going to be 6 multiplied by minus 743. I'm then going to go to the water molecules. Now each water molecule has got 2 O to H bonds, but there are 4 molecules. So it's going to be 8 O to H bonds in total, which is going to come back as 8 multiplied by the O to H bond strength, which is 463, but it's a negative because I'm bond making. So once I've totaled all of those up, I put them in the calculator and hopefully I should get minus 8,162. Now, this is the important bit. Remember, once we've done all this, where we've made the bond breaking positive and the bond making negative, it is essential then that we take the sum of the numbers. Okay, so it's bond breaking plus bond making. Okay, so it's positive 6,482 plus minus 8,162. When I put all them together, hopefully if everything's been done properly, I should have a minus 1680 kilojoules per mole as my answer. Okay, so it's an exothermic reaction. Okay, and the reason why it's exothermic is because the bonds that we make have greater strength than the ones that we have to break. Okay, notice we took the sum of the numbers. Okay, by us being clever and putting our negative numbers in there, what we've been able to do is that then carries through and I don't have to do bond breaking minus bond making. I just add the 2 numbers, okay? And that's going to become more apparent when we do some of our examples where we have to find unknown bond strengths. So that's example 2 done. We'll look at another one now. Right, so this is example 3. Now, we're deliberately looking at an example where you've actually got to work an unknown bond out now. So in the previous ones, you've been working out your bond breaking, positive number, working out your bond making, which is a negative number, taking the sum of the 2, and that gives you an answer, job done. But we're going to change it now because the examiners in the last 2 or 3 years have started to sort of move more commonly to asking you to find a bond that's missing and giving you the answer and having you work backwards, which is quite tricky. But the method is still the same. So you still start off by highlighting your reactants. So this particular question is asking me to find the unknown bond strength of the carbon to hydrogen bond. So that's the one I'm trying to find. We don't know what that is. So I'm going to highlight the products in a different colour. We'll go for orange for this one. We'll be a bit daring. And the thing that I would say is the most important thing is they're looking for your logical working out. Okay, so that's important. Now, what we're going to do, we're going to follow the same method, but we're going to have to just create an equation at the bottom, which I'll show you how to do. So the first thing to do is we've got 2 carbon to carbon bonds, which are given in the table as 2 times 347. Now, I've also got 8 carbon to hydrogen bonds. Now, they're my unknown, so I'm just going to pop them down as 8x. And then last but not least, I've got my 5 oxygen to oxygen bonds, which I've been given as 4 times 598. Now, this part now is quite tricky, and I think a lot of people find this bit hard. What I'm going to do is I'm going to work out the two yellow numbers. Okay, so I'm going to work out the 2 times positive 347 and the 5 times 498. I'm going to work both of them out to give me one number. Okay, now what that does, it allows me to make the equation easier to solve. So I've got my 8x, which is my unknown, plus this number from the two highlighted parts. Now, when I add the highlighted parts together, it's 3,184. Okay, I'm going to leave that down there, and I'm going to deal with my bond making side now. So the bond making side, we've got, like we had in the previous example, I've picked the same one because it makes it easier to follow. We've got 6 C double bond O bonds to break, which is basically 6 times, now I've got to be careful here because it's going to be minus 805. Now, the second part, I'm going to have 8 O to H bonds, which is going to be 8 multiplied by minus 464. Now, all of that lot added together will give us another number, which is 8,542, but it is minus because it's bond making. Okay, so I'm just going to highlight that orange just so that makes things a little bit easier to see. So what does that mean in terms of my equation? Well, I'm going to bring down the number to the bottom. So that minus 8,542 is going to be put on. So I've got over here, I've got my bond breaking, which is my positive values, and then I've got my bond making value, which is negative. And all of that added together equals the answer, which is given to us up here, which is an exothermic reaction. Now, for those that are unaware, an exothermic reaction means it is a negative number. So they're being quite sneaky here. They're expecting the candidates to know that that means the answer is minus 2219 kilojoules per mole. Okay, so down here my final answer is minus 2219 kilojoules per mole. So what we've got to do now is we've got to work out the value of x by rearranging the equation. So there's a few ways we can do this, but essentially what will happen is when you move everything around, you should get 8x is equal to 3,139, which then means x is equal to 3,139 divided by 8, which should give you an x value of 392 kilojoules per mole. So this question would be potentially up to 5 marks in an exam. It's a challenging question. Now what I want to do for this is just make you aware of a couple of points. The first one is the numbers that we've used. Because I've used the same example for question 2 as I have for question 3, you might notice, and these are real exam questions by the way, you might notice that the values are somewhat different sometimes. So if you look at the carbon to oxygen double bond, it's slightly different on this example than it was on the previous one, and that's because bond enthalpy values, they're average values taken over a range of different compounds, and some books quote different data values to others. But for you in an exam, you will just use the data that you're given. That's what you do. So this point here, the 8x plus the 3184 minus 8542 equals negative 2219. So from that point onwards, there's basically a period where you've got to rearrange that equation to get 8x on its own. And that just requires a little bit of mathematical manipulation. We'll look at another example of this in example 4 in a second. Right, so example 4. This is another one where we have to find the unknown bond. We've been given the answer, we've got to work out an unknown bond, but this time the bond is on the product side and it does change things a little bit, and this is why we use the method we did earlier in the video where we made sure all of our bond making values are minuses, and we're going to show you the importance of that now with this example. So we've got bromine reacting with methane in sunlight. The diagram below shows the displayed formulae for the reaction, and the table below shows the bond energies. Obviously the unknown one we're trying to find is the carbon to bromine bond. So that's the unknown. Now the eagle-eyed amongst you will notice that that bond is part of the products here. Now that's important because that is going to mean that when I do this calculation, I've got to ensure that this is a minus x. Okay, we're going to look at the relevance of that and how we're going to approach this in a second, but that's the premise of what I'm going to do. So first of all, I'm going to highlight my reactants in one colour, put them in yellow, and then I'm going to highlight my products in a different colour. Again, options of highlighters are your own choices. You don't have to use the same as me. So we're going to start with bond breaking. So our bond breaking is essentially a pretty straightforward one here because there's not that much going on. So I'm going to write them in a list and I'm going to transfer the values out in a second. So I've got 4 carbon to hydrogen bonds, okay? So that's going to be equal to 4 multiplied by the carbon to hydrogen strength, which is 412. I've then got 1, I'll get rid of those 4. I've then got 1 bromine to bromine bond, which is 1 times the Br to Br bond, which is 1 multiplied by 193. I then work all of those out. Now when I've done all the number crunching there, I get 1841, and it's a positive number. We'll come to the relevance of that in a moment. So that's all done. So I'm then going to go to the other side, the bond making. So the bond making, remember all of these values have got to have minuses in front of them. So I've got 3 carbon to hydrogen bonds on this side, which is 3 multiplied by minus 412. So that's them 3 done. I've then got a carbon to bromine, which we're going to call X. There's only one of them, so that's just going to go down as a minus X. Now, the reason why it's a minus X is because it is on the product side. Okay, that is why I've got to put that minus in there. If it wasn't on the product side, it would have been a positive. Okay, so all of these numbers are negative. The last number that I've got to get is the hydrogen to bromine bond, which is 366. So 1 times H2Br, which is 1 times minus 366. Now, what I would strongly urge you to do in this now is these 2 numbers that I'm going to highlight in orange. I would strongly recommend that you work out those 2 numbers. Okay, so 3 times 412 and the 1 times minus 366. Okay, you can work them out. It's going to make life a little bit easier on the final bit that we do in a second. And we're going to go through how you then take this into an equation and find x. Right, so how do we manipulate this to get the answer that we need to get? Now, the first thing I would say is on our bond making side, I want to just turn these 2 numbers into one number. Okay, so the minus 412, which I'm timesing by 3, and the 366, which is a minus, is going to give me a total amount of negative 1602. Now I've done that for a reason. The first reason I've done that is to make life easier. By turning both of those into one number, it's going to make the equation easier to manipulate in a moment. So what I do now, and this is quite an important step, I write an equation as if I would do in maths, and all of my bond breaking values are going to be positive. Now thankfully I've only got one, it's 1841, so that's going to go in there as positive 1841. All of my bond making values are going to be minus. So I've got the minus 1602, which is straight from there, and I've got the minus x. All of that is going to equal the answer to the question which is given to us on this right hand side here. So that is negative 51. So once I get to this point, it's 1841 minus 1602 minus x equals minus 51. Now let's just clarify a couple of points. These numbers here, the minuses, the reason why they're both negatives is because they have come from the bond making side. So these numbers have come straight down from there. Negative, and then this 1602 is negative. The reason why the other side is a positive 1841 is because that is a bond breaking. So these guys are bond making, that's why they've got negatives in front of them. The answer is just taken straight from the question, minus 51. I haven't had to do anything with that, they've given me that. Okay, but those two numbers are negative for that reason. Now, for a lot of you guys, you'll be able to solve that and get X. You know, your maths teachers will have shown you how to do that. If you're not sure, I'm going to show you a method that I use that sometimes I find easier. But by all means, just use whatever method you feel to get X. Now, if I highlight all of these guys in yellow, I can turn them two into just one number. So the minus 1602 and the positive 1841, I can turn them into just one number, which is 239. So 239 minus x equals minus 51. So all I've done, I've just sort of combined the two numbers to give me 239. I've just literally done positive 1841 minus 1602 gives me 239. So 239 minus x equals minus 51. And then it's just a case of finding x. X will then be positive 290 kilojoules per mole. Now, when you're in an exam, you're not going to know if that's right. Okay, you're not going to have an idea. I mean, if the number is between sort of 0 and 950, because that's the strongest bond, the nitrogen to nitrogen bond, you know, if you're getting X values of 2000, then you know it's wrong. It shouldn't be more than 1000. It's unlikely to be more than 800, to be fair, but certainly not going to be more than 1000. But if you're unsure, take the value and substitute it back in and do the question the normal way, and you should get an answer of negative 51 if you've got it correct. So that there is a 4-mark example, and obviously quite tricky, but if you follow the method through, then you can pick marks up. If you are absolutely struggling, if you work out the breaking bonds, work out the making bonds and your X, you'll still get some credit, possibly get 2 out of 4 for just working those out. So try to obviously follow it through to the end if you possibly can, and get that value, and then just at the end substitute it back in and see if it works. Alright, so we're going to give you a chance to have a little bit of a practice with one of these now. So this is a normal standard one where you're given all of the bond strength and you've got to work out the energy change. So if you want to pause the video and have a go at working this out, then in a couple of minutes I'll go through the answer. Right, hopefully you've had a chance to work that one out when you've paused the video. I'm just going to talk you through how we would do this. So first of all, we highlight our reactants in one colour, so we've done that. And then we highlight our products in another colour. And then it's just a case of us working out bond breaking on this side. So our bond breaking values, which should be nice and easy because they're all given to us. So I've got 4 of these molecules with the N and the 3 H's. So within that molecule, I've got 3 bonds, but there are 4 of them. So in total, I've got 12 N2H bonds, which is going to be 12 multiplied by 3 491. I've then got 3 oxygen molecules, O double bond O. So 3 O double bond O's is going to come in at 498. So when I work out all of those added together, I should get 6186. Now over to bond making next. Now bond making should be the same, but remember all of my values should be negative numbers. So I've got this N triple bond N, which is 945, and I've got 2 of them. So 2 times minus 945. And just as a sort of an aside, this bond here, the nitrogen triple bond nitrogen, that's the strongest bond you're going to come across in these calculations. So if you are doing the calculation that we did previously where you're working out an unknown bond, if you get a number that's above 945, or certainly above 1,000, it's categorically wrong, because that's the strongest bond that we know, the 945. So you shouldn't be getting a value bigger than that if you're working out an unknown bond strength like we did in example 3 and 4 earlier. So the next molecule in orange is our water, and within the water there's 2 O to H's, but there's 6 in total. So 6 times 2 gives me 12 O to H bonds to form. So 12 times minus 464, and I total all of that up, and it gives me a number which is minus 7458. And then all I need to do, it's as easy as taking the sum of these 2 numbers, and we know that we add them together because we've already put our minus in there. So if you work all of that out and you do 6186 plus the minus 7458, hopefully you've got minus 1272, and they've already given us the units, so that's nice and easy. 3 marks in the bank. Job done. Right, so hopefully you've had a good chance to have a practice that first one, and we can have a go at this second one. So this is another example. I'm just going to give you a minute or so if you just want to pause the video. This one is slightly different because you've got to find the unknown bond in this one. So it's like the examples 3 and 4 that we did earlier in the video. So if you just want to pause the video and have a go, and I'll go over it in a minute or so. Right, we're going to go through this one and we'll talk through how we would approach this. So first and foremost, I'm going to highlight, as always, the reactants in yellow, and then I'm going to take a highlighter and highlight the products, in this case in orange. So we're going to just do exactly the same as what we've done before. We've got our bond breaking, which we're going to do down at the bottom. So our bond breaking, so essentially we've got 4 C to H bonds. So our 4 C to H bonds, which is 4 multiplied by 412. We've got a carbon double bond carbon, one of. So 1 carbon double bond carbon, which is 1 times 612. And then we've got our unknown, which is our bromine, which we're going to call X. So we'll put X there as well, just one of them because there's only one. Then we go to our bond making side, and all of these are negative. So CHs I've got 4 of. So it's 4 times C to H, which is 4 times minus 412. I've then got a carbon to carbon single bond, one of them, which is 1 times 348. Notice that a double bond is not necessarily the same. It's not necessarily double what a single bond would be. I forgot my minus there, so it's 1 times minus 348. And then I've got 2 carbon to bromines, which are final ones. So carbon to bromine, 2 times minus 276. So what I'm going to do to make life a little bit easier for myself, I'm going to highlight the numbers on this side and I'm going to turn them into one value. So on my bond breaking side, I get 2260 for that. And then the blue, which all my bonds formed, are going to come in at minus. Now I've got 2548. So just to be clear on this, what we've done, I've collapsed all of them values there, all of those guys, into just one number, the 2548. Now, what I have to do next, I have to write my equation sort of in a mathematical way so I can solve it. So what I'm going to do, I'm going to do my bond breaking first, which is 2260 plus x. Notice I'm using the plus x because it's bond breaking that it falls on. And then all of my bond making are going to be negative numbers. And I've only got one, and it's going to be minus 2548. And that will all equal the answer, which is the overall energy change, which has been given to me, which is minus 95. Now, my personal preference at this stage is to bring together all of the numbers on one side. So the 2260 and the minus 2548. And when I put them together, 2260 and minus 2548, that gives me minus 288. So basically I'm left with minus 288 plus x equals minus 95. Right, so to finish this off, we get x is equal to 193 kilojoules per mole. And as always with these questions, when you're in an exam and you don't know the answer, you can't look it up, you always sub the number back in and just triple check that it's worked, and it should give you the answer that you get of minus 95 if you put x in. So that is that one. I'm going to show you one other just to finish off with that's a little bit tricky that I'm going to talk through that's never been asked, but if it did, it just gives you an idea of what you would do, because I think it would cause a few problems. And we just never know with the examiners how they're going to approach things, so it's just always good to be on your toes and ready for anything sort of variation wise that they could ask you. So we'll do that in the final example. Right, to finish off with, I thought I'd show you this one, and quite a tough one, and it's got unknowns on both sides. Never been asked at GCSE, but did come in on one of the A-level exams. So it's just something a little bit different. Not that tricky if you follow the method, but just something to think about. And hopefully you can follow what we do. So I'm going to talk you through it. Table below contains some mean bond enthalpy data. So we've been given a bunch of values. It then says use the following equation and the data to find the CH bond enthalpy. Now you'll notice that CH appears on both sides. So what we're going to do, we're going to highlight our reactants, as we do, and we will then highlight our products. Now, what we've got to remember is the answer of minus 136 has been given to us. I've got to try and work out what the unknown is using that. So I'm going to start off with the bond breaking. So I've got CH is my unknown, so I'm going to assume that CH is X. So on this side I've got 4X. Hopefully we're all happy with that. 4 bonds. I've then got a C double bond C, which comes in at 6 112. So I'm going to add that. I've then also got a hydrogen to hydrogen, one of them, which comes in at 436. Now, this is where it gets a little bit tricky because everything on the other side, as we recall, should always be negative. Now, I've got CH on this side as well, but this time I've got 6 of them. So I'm going to have a minus 6x. Now, the reason why it's 6 is because there's 6 CH bonds. The reason why it's minus is because it's on the product side. I've then got the C to C single, which will be minus 3, 4, 8. And all of that equals minus 1, 3, 6. Right, now to bring this through to the end, what I'm going to do, I'm going to highlight any numbers and x values. So the x's I'm going to highlight pink. So I've basically got 4x minus 6x, and that is going to give me minus 2x overall. I'm then going to take all of the numbers on the left side. So I've got 612, positive 436, and negative 348. And they are going to become, when I add them all together, they're going to become positive 700. So that's me adding all the blues, the positive 612, the positive 436, and the negative 348. And the other side, the minus 136 remains the same. So then, essentially, I end up with minus 2x equals minus 836. So x equals minus 836 divided by minus 2. Therefore, x equals 418 kilojoules per mole. And as before, if I get that number, what I can do is I can substitute back in and see if that works, and I should get the answer of minus 136. Now, honestly, hand on heart, do I expect that to come on a GCSE? No. Would I be shocked if it did come at the end of a higher tier paper, a grade 9 question? No, I wouldn't be shocked. But it's just to give you an idea, you can have numbers on both sides. It's all about manipulating the equation, being consistent with your negatives, making sure that any bond making is given a negative number, and then just solve the equation from there. Always sub back in at the end, because that just gives you that reassurance that you've got it right. So hopefully the video has been helpful, guys. We've gone through a few examples, and hopefully you've a good understanding of it.